thrilled to welcome our next speaker, Suha Qayyum from Saudi Aramco. Suha Qayyum is a research and development engineer with experience in upstream solutions over a career spanning more than 10 years. Suha has experience in developing Saudi Aramco's in-house reservoir, gigapowers, basin, terabazine, and seismic simulators, GeoDrive. Her area of expertise is in increasing discovery and recovery by leveraging different disciplines, including simulation, high-performance computing, artificial intelligence, and predictive analytics. At Saudi Aramco, Suha has championed several digital transformation projects in the reservoir simulation division, led teams in digitization of core analysis workflows, and employed machine learning and NLP to automate petroleum engineering-related document analysis. Her most notable achievements include designing and receiving a patent for a novel algorithm that enables the world's first 1 billion cell basin simulation run. At the center, Suha was the first female champion in advanced scientific computing, tasked with accelerating the evolution of software algorithms and technology to enhance the company's reservoir simulator performance, robustness, and efficiency. Her groundbreaking work led to reduced costs and an increased recovery and several patents and publications. Suha serves as SPE Saudi Arabia Section's Young Professional Chairperson for the period between 2018 to 2019, and the SPE Subcommittee Co-Chair for the International Petroleum Technology Conference in Dhahran in 2020. She has participated in several panels and given a keynote speech. She has been awarded several awards, such as the Emerging Leader Global Petroleum Show Award in Calgary, the SPE Regional Young Member Outstanding Service Award, and the Young Outstanding Professional of the Year at Expect Art Award. She holds master's and bachelor degrees with highest honors in electrical and computer engineering from the Georgia Institute of Technology. I am very thrilled and excited to welcome Suha to our Women in Data Science workshop, and we are very excited for her talk on machine learning impact on reservoir simulation.
Thank you so much for the introduction. I just want to first make sure that I'm heard. Can you hear me?
Yes, we hear you.
Okay, great. And can you see my slides?
Yes, we do.
Excellent. Okay, so we're good to go. All right. So
yes.
Good evening, ladies and gentlemen, and good morning to everyone on the other side of the globe. I'd like to sincerely thank WiDS KPPM affiliate for the invitation. And I would also like to thank Saudi Aramco for allowing me to participate in the event. I'm really thrilled. Actually, it's almost like me and Dr. Manal had spoken about our presentations, and we have them aligned, because really what the presentation she gave today saves me a lot of trouble of explaining upscaling and some of the techniques that we use at Saudi Aramco that I will be introducing in my talk today, which will be basically sharing the ways that artificial intelligence can alleviate the load off of high performance computing in the context of reservoir simulation. But really, some of these techniques can be applied into other domains of simulation. So I'm assuming that the audience is of course, very knowledgeable in data science, but I will dive a little bit into what reservoir simulation is. Reservoir simulation is very heavily used at Saudi Aramco. As you may know, we actually have championed reservoir simulation in the world, really. And what it is that we routinely use it within our reservoir management activities to design, forecast, and optimize our oil and gas production operations. What we do is we study the flow of hydrocarbons, or the fluid flow in hydrocarbon reservoirs under production conditions, so the way that oil flows, water, and gas. Of course, for this, the simulation in this context involves the solution of numerical approximations to the highly nonlinear and coupled systems of partial differential equations. These equations govern flow and transport within the subsurface, as well as the wells that are connected and surface facilities. So it's a very nonlinear system that we're solving, and it's very complex. So of course, well, we have unique challenges at Saudi Aramco and in Saudi Arabia in general, and this is what really motivated us to develop our in-house reservoir simulator. And one of these unique challenges is that our fields are huge compared to the rest of the world. It's a challenge, but it's also a blessing, right? But really, our typical industry reservoir simulator in the world is approximately, it can range to about 10 kilometers in size. However, in Saudi Arabia, we have our largest reservoir, which extends about 280 kilometers from north to south, which is Reservoir. And because we have this unique position in Saudi Arabia, this results in us needing to create models that are representative of those 100-kilometer long fields. And this is similar when you compare the size of a ping pong table, as you can see in the picture, to a football field. And this illustrates how unique physical dimensions of our hydrocarbon reservoir creates a need for unique software capabilities that are capable of handling such large problems. So one of the dimensions of our challenge is size. The next dimension is that we have to, when we discretize these models, we have to have enough or adequate resolution to give us meaningful results. If you look at the image of the peacock, the zoomed in image, this is at a, you can say a coarsened image. However, if I were to look at it with a higher resolution, certain attributes can be seen and more clear. Very similar, we can actually translate this to the results that we get from our reservoir simulator or simulation in general. For example, you can clearly see in the top right image that if I were to use a higher resolution, certain oil patches or oil saturation can be seen. So more cells lead to more accuracy. This phenomena is even more emphasized when we are close to the near wellbore area. So as you can see in the bottom right image, coning, which is a production problem, can actually be predicted more accurately with higher resolution. So with this capability, we can maximize our production and maximize the sustainability from our reservoirs. And because of these unique challenges, as I've mentioned, I want to walk you through the history of reservoir simulation at Saudi Aramco. These are snippets from media and different news outlets. We embarked on our first version of our parallel oil-water enhanced reservoir simulator that we released in the 1990s. It was known as POWERS. It was with the intent of simulating our reservoirs and to be able to have the adequate resolution. So we were in the million range back in the 90s. However, we then coupled our simulator with, of course, high performance computing. So that's parallel machines that are running at the same time, solving one problem, but they're all working together to solve it. And we were able to scale after that. And so we were able to increase to 100 million. And then we reached 1 billion in 2010, and that's when we released gigapowers. Of course, our ambition did not stop there. We're always after increasing our resolution, also increasing the size of the models that we can simulate, because we can actually, with having that capability, we can even have different fields that are connected together. And with that, we can see if these fields are talking to each other. And so therefore having more accurate results and more information that we can get. And so you may have heard that in 2016, we were able to use the cow system, Shaheen, and with that, we achieved a world record where we were able to simulate and a proof of concept that we're actually capable of reaching 1 trillion cell runs. This was a part of the reservoir simulator. It was not the full simulator, but we're well on our way to release our next version, which will simulate trillion-sized cells, terapowers. And with terapowers, we will also be working on discovery. So that's where the basin simulation that I was working on is also going to be coupled. So it will be a reservoir and basin simulator all in one. So now that I've walked you through the history of reservoir simulation, we can also now see what are the workload challenges. So I've mentioned that we're trying to scale in size, and we're trying to discretize these problems into very small or in other very small cells, in other words, higher resolution. And so our workload challenges is that I spoke only about the simulator, which is really the heart, but we run this simulator thousands of times. Why? Because in reservoir simulation, we have measured data that we acquire from our fields. This measured data, however, is not for the entire field, it's for certain parts. And what we need to do is we need to calibrate our models to make sure that we are having our model being representative of those measured data. And so that is what is called as history matching. So we calibrate the model until we match our measured data. After that, we start from today's date, for instance, and we start then doing the next cycle, which is predicting the future. So we run different cases predicting that, you know, what if I drill here a well? What if I inject water here? What if I inject gas instead of water? Will I reach my production targets, or will I maximize my production? Will I sustain my production for as long as possible and then increase my net present value? And so that's what's known as the plateau. And therefore, we're running thousands of simulations. You can imagine that. And because our models are huge, we're starting to now think that resources are really finite. So we can keep on scaling, but then if we want to scale in terms of the number of simulations that we run and the answers that we get, the insights that we get as quick as possible, we need to start thinking in other ways. So in this little plot here, I showed that the beginning part, you know, we're matching the X's, that's our measured data, but then in the future, we're going to start looking at different studies, and that's our forecasting. It's also worth mentioning that our model sizes have been increasing in the past 20 years by 600 times as we acquire more data and have higher resolution. And our number of runs have increased 50 times in the last few years. And therefore, we now want to look at tackling this problem a different way. So as I've mentioned, a recap, simulation provides key insights into system behavior and performance. We have been using high performance computing coupled with simulation, but now this is where data science comes in and machine learning. We're thinking we need to really couple artificial intelligence into simulation and high performance computing to alleviate the load off of high performance computing. And in the rest of my slides today, I'll be diving into and sharing some examples of how we can fuse artificial intelligence with simulation that's already been happening in the past few years. And these examples are from Aramco, Aramco's research work, different companies in the oil and gas industry, and even other related industries. And hopefully with this, I can inspire all data scientists to think how they can help other domains into decreasing the workload by maybe running less simulations and maybe even replacing some simulations. So I've categorized it into 5 focus areas, and that's what we're going to be focusing on. How can we accelerate some of our workflows? How can we even replace parts of our simulation if those parts of the simulation are taking too much time and maybe their accuracy is not as important, so we can get quicker instant results and couple that with our simulation, maybe even replacing the entire simulation. Improving our performance and accuracy. There are certain ways you can do that with machine learning, and also how do we select the optimal grid size? So Dr. Manal showed that upscaling is something that's beneficial, but sometimes you need to, when I'm talking about upscaling, I'm talking about the cell sizes. So of course, if you increase your cell size, you can have less computations, but then how do you select the optimal grid size? And we'll look into each of these, beginning with accelerating workflows. So history matching, as I've mentioned, was that beginning portion where we're trying to match our measured data. This is the process of building one or more sets of numerical models, and we account, of course, for our observed or measured data. So we calibrate the models, and typically naive or simple methods are used. People just, say, let's just run these history matching with varying, X, Y, and Z parameters. However, sometimes this results in unphysical realizations, and we end up with wasted runs that don't honor the geological features. And so, choosing which simulation to run and which parameters to use can really reduce our search space and really reduce the number of simulation runs. A paper that I'm citing here is one where Stanford has used convolutional neural nets with something known as principal component analysis, where they were able to reduce the dimensionality and basically reduce the uncertainty by using this method that honors complex geologic features. So they coupled those two together and were able to physically have more feasible model realizations. And with that, they were able to predict which parameters are more likely to result in the desired changes, alleviating a lot of the load off of running simulations and running unnecessary simulations. So really smarter parameter selection from the search space versus just accelerating our individual simulation runs. You can have a simulation run, maybe takes a long time to run. However, if you reduce the number of runs that you need, you're actually then speeding up your entire process. And so that's one way of speeding up the workflow. Another example is automatic well placement. In this image here, I just wanted to explain what really goes on in the reservoir. So you can see that the middle well is injecting water. This then helps with movement of the oil and then producing the oil. It's a very simplified video, but I just wanted to explain that here, if you have a homogeneous reservoir, then having your wells in that location where it's almost like a box is maybe the most optimal. However, really, if you're looking at a heterogeneous reservoir, which is a real reservoir, the combinations are endless. And where do you begin? So when you look at this top left image, you see that it's a homogeneous reservoir. So maybe having your producers on the corners is the optimal solution. However, when it's heterogeneous, then as you can see here, I don't know if it's small, but I'm going to try with my mouse to show you P1, P2, P3. Having it in different locations that are almost random is actually more optimal. And so this is something I'm actually right now in the reservoir simulation department, and this is something that I'm seeing that is something that maybe we're still manually doing, and it's still a very hot topic. So also one thing to know is we want to also reduce the number of wells, so because drilling wells costs millions of dollars. According to U.S. Energy Information Administration, it costs about $5 million to $8 million to drill one well, and this is only onshore, and offshore is even more expensive. So as I've mentioned, it's exponential possibilities to test. Machine learning can assist experts to evaluate the performance of new well locations and even the configurations of the well. So how much do you want to, what is the rate of the well? How much do you want to inject? All of these answers can be reached with machine learning. So this paper actually trains machine learning regression algorithms, and it predicts the final cumulative production of new trajectories. But however, they've only were successful on synthetic data, but not real field data yet. As I've mentioned, you would have to train thousands of simulation. And because of this problem being so complex, the manual placement is still the most common. However, there is still room to improve in this automatic well placement. I know that we're doing a lot of brute force techniques, but I think with machine learning, we can definitely, we definitely have room to improve in this field. So now I'll move on to replacing parts of simulation. One very interesting machine learning or learning method is reinforcement learning. I'm sure you've heard of Go. This is a ancient Chinese game, and reinforcement learning has actually been used to teach a computer to play AlphaGo and to improve its skills by combining it with combining neural network with a powerful search algorithm. Basically, if this is maybe the only part I'll dive in a little bit into machine learning, because I know that most of you are experts in data science, but basically it's basically there's an agent which interacts with an environment, and there's basically a goal, and that's basically the ultimate goal, and that's also the reward. And basically the environment evaluates the action and it presents the agent with a new state and the reward, and this just keeps going on and on in a loop until you maximize your reward and you learn from it. It learns from itself. And this basically has resulted in the strongest Go player in the world. Reservoir simulation can definitely adopt the same technology for, in general, and specifically what we found for well optimization. So we have actually prototyped this in Saudi Aramco, but I recently found a really cool publication called Eclipse Gym. This is it's open source on GitHub, and it's a reservoir simulation environment for reinforcement learning. And it basically, you can couple it with your reservoir simulator. They couple it with Eclipse, but it can work with any simulator. So what we want here is to determine the best production and injection rates. So in this example, was applied to a synthetic case with 4 injectors, 1 producer, as you can see on the top right. And with reinforcement learning, we basically, we can basically use it instead of a well management optimizer, for instance. Just to tie in with the reinforcement learning, in reservoir simulation, the wells are your AI agent. the reservoir simulation model itself is your environment. And of course, you can have unlimited number of wells or agents. And the reward is your oil recovery, or for example, your net present value. And in this case, we want to maximize that. And so we actually were able to, with reinforcement learning, a very preliminary proof of concept, we were able to have the water reach producer well at the same time. That was our reward system. How can it reach at the same time and produce and maximize the oil production? So this is a very promising technology that can be used in reservoir simulation. We've actually also, in 2018, we were able to prototype using machine learning to replace phase equilibrium calculations. So in reservoir simulation, we have our black oil, but also we can also describe our model instead of just saying oil, water, and gas. We can actually dive deep into the components. However, for that, you would have to do what is known as a phase equilibrium calculation or a flash calculation. So here we developed an algorithm that reduces the cost of phase equilibrium calculations for compositional models by applying machine learning. And what it really uses is what is known as relevance vector machines and artificial neural networks. And 3 fluid data sets were basically tested, and the speed up was about 20% with an error of 0.01. Of course, then you have to outweigh what, your error versus your speed up. With an error of 5%, we were able to reach a 90% speed up, which is incredible. And we were able to then replace the phase calculations with a machine learning model. This now brings me to replacing simulation. I was very intrigued with this, and I've actually found that in the computational fluid dynamic realm, it actually has shown to show very good results. This was achieved in 2016 as a milestone by Autodesk researchers, where they replaced lattice-Boltzmann method calculation for solving flow with a neural net. And this neural net gave results instantly, of course, instead of using traditional CFD simulations. It's a very physically difficult problem to solve, and it's computationally expensive, very high in memory demand. But with this, they were able to reduce their speed, their time taken, and increase their speed, and also have a very small margin of error. So similarly, reservoir simulation is about this uncertainty quantification, and we are, as you've seen, we're running different scenarios, and we end up choosing one scenario over another. So having this relative scenario type of calculation, we can actually have a margin of error. It's actually acceptable, especially when we're just doing a relative sensitivity analysis. Also, the University of West Virginia has been very heavily involved in using proxy models and neural nets instead of running simulations. And they use artificial intelligence and machine learning techniques. These proxy models are basically aimed at generating the output of numerical flow, fluid flow models in a very short period of time. In this work, the proxy model was actually used for a real case of CO2 sequestration, which is a very important type of project. And of course, under different CO2 injection scenarios, the data-driven model was developed to generate pressure, saturation, and CO2 mole fraction. And with this, they resulted in very less computational effort and considerably shorter period of time, of course, compared to numeric reservoir simulation models. So what they've shown is that it took 15 minutes to execute one simulation run, but with this neural net, they were actually able to get their results in 45 seconds, which is a 2 times speed up. And I'll be showing an example of improving performance and accuracy. So as Dr. Manan mentioned, when you come to solve porous media, you're basically solving a nonlinear system. And in reservoir simulation, of course, it's no different. You're solving a nonlinear system that we decouple and linearize, but then always have to make sure that we are converging in our nonlinear system. So it's a very intricate process. And of course, we select time steps. These time steps are usually selected using different, basically physical constraints, such as previous number of linears, number of newtons, maximum pressure of any cell, for example, maximum normalized saturation changes. However, what we've done, and this was work that was done at Aramco, it's currently in production even, was to use fuzzy logic to select our time step size. And with this, we were actually able to reduce our time step cuts, because as you know, if we're running our simulation and we're not converging, then reducing our time step size can result in smaller load increments and smaller nonlinear effects, which helps in convergence. However, it is wasted when you reduce your time step, try to converge, and then you don't, then you go back and you have to reduce your time step again, try to converge, and you end up with a lot of wasted iterations. And of course, your runtime would be much larger. So with fuzzy logic, which is basically an approach that instead of having a true or false answer, you have a degree of truth. And with this, we were able to calculate our time steps more accurately and basically reduce our runtime and increase our robustness for our very challenging nonlinear simulations. This brings me to the last pillar, our optimal grid size selection and how AI can be used to select that. So intelligent gridding is something else that we have developed also in-house at Saudi Aramco. And just a recap, as you know, more data and more ones are needed. Our simulation models are very fine grid, but as you know, resources are limited. So our motto is to automatically have the right resolution of grid in the right place. And you can see on the left, this is using basically a heterogeneous grid discretization, whereas on the right, it's very homogeneous. And of course, you would basically take away from accuracy if you're upscaling in the wrong places. If you're upscaling in areas where you have very high oil saturation, then you're definitely going to have results that are not as correct. Whereas if you're towards the aquifer, so you're away from the wells, then you'll have more correct results. However, using artificial intelligence to find that or to help you select that is more robust, because I myself was actually working on using this for a reservoir, and I was upscaling away from the wells, but then I didn't realize that we actually had a lot of channels in that reservoir, and so then that phenomena of being away from the well, then you're good to upscale was wrong because of the channels. So even if you're away from the well, you still had your channels of which were carrying your oil, and basically we had to upscale away from the channels as well. And so using machine learning to find that would be very beneficial. We're actually working on that right now, and I just wanted to showcase how important this is. So you can have your matching results, however, by reducing your elapsed time completely. So even reducing your resources, and that's something that we're doing currently right now. We have models that we used to have to run 2,000 cores. We can now run those same models with 100 cores, giving you 50 times less turnaround time and using 20x less resources. So this goes back to that resources are finite. So these kind of techniques are really needed and beneficial. And again, you could go get away with some inaccuracy, because again, if you're doing realization and you're doing sensitivity analysis, so having more data points is probably more beneficial than having that one very accurate data point. And you can run these models. It depends, of course, on your intent. If you're running for sensitivity analysis, then upscaling is probably a very good way to go. However, then you can reflect that back to your fine grid model, and then from there get your accurate results. So with this, I've come to the end of my talk. I know it was a lot of material. I was trying to make it as high level as possible to share with you. Basically, the recap is traditionally we've been using reservoir simulation, and we've been benefiting from our increased resolution, incorporating more physics. However, I think it's time to capitalize on artificial intelligence and incorporate them in our classical workflows and within our simulations. However, strong domain knowledge is very critical ingredient. So basically, it's a very multidisciplinary. If we want to achieve these very impressive results, we need to work together as multidisciplinary. So data scientists, data engineers with reservoir engineers or simulation engineers to identify these possible areas of application and determine the best use for transforming these innovations. But we do see that replacement of parts of simulator and even the entire simulator is very much in our near future. And with that, I would like to thank you for your time and open the floor to any questions.
Thank you very much, Suha, for the very interesting talk on using artificial intelligence for the domain of reservoir simulation.